Welcome to our guide on securing cloud data, techniques and best practices. This chapter is critical for the Google's PCA exam. You can find the chapter parts in the description. Feel free to jump between chapters to review your needs. Let's start with securing compute engine techniques and best practices. 1. Service accounts, IAM roles, and API scopes. Service accounts. These are like user identities for your virtual machines, VMs. When a VM needs to access Google Cloud Services, it does so through a service account. You can assign roles and permissions to these accounts to control what they can do. The idea is to follow the principle of least privilege, giving only the necessary permissions to each service account. Default service account. When you first use Compute Engine, a default service account is created, usually with broad permissions, Project Editor. It's important to reduce these permissions to avoid security risks. IAM roles. These define what actions a service account or user can perform. You should always assign only the necessary roles to ensure security. API scopes. These limit which Google APIs the VM can access. For better security, avoid granting full access to all APIs and instead restrict access to only the ones the VM needs. 2. Managing VM logins. Linux VMs, accessed via SSH, secure shell, using a username and SSH key for authentication. Password authentication is usually disabled by default for security reasons. Windows VMs, accessed using RDP, Remote Desktop Protocol, and a username-password combination. SSH access. You can connect to Linux VMs using SSH from the Google Cloud Console, Cloud SDK, or third-party SSH clients like PuTTY. For VMs without external IPs, you can connect through a VPN or use Identity-Aware Proxy, IAP, for secure connections. OS login. This is a recommended method for managing SSH access to VMs. It ties user access to Google Cloud IAM, making it easier to manage users across many instances or projects. It also supports two-factor authentication, 2FA, providing an additional layer of security. 3. Organization Policy Controls. Organization Policy Service. This service allows you to define policies that apply to all projects within your organization. For example, you can enforce which VM images can be used by setting up a Trusted Images policy to ensure that only secure, pre-approved images are used to create VMs. 4. Shielded VMs and confidential VMs. Shielded VMs? These help protect VMs from advanced threats like remote attacks and privilege escalations. They ensure the VM's integrity by verifying its boot process. Shielded VMs use secure boot and measured boot technologies to prevent unauthorized code from running during startup. Confidential VMs. These provide additional security by encrypting data even while it's being processed, called encryption in use. Confidential VMs run on AMD EPYC processors, offering high performance with minimal impact on your workloads. They are ideal for highly sensitive workloads, such as financial data or healthcare applications. 5. Certificate Authority Service. Certificate Authority, CA. Service. This service helps organizations manage private certificates for internal security needs. Instead of manually handling complex certificates, the CA service automates the process of issuing, managing, and revoking certificates. It also integrates well with Google Cloud Services, reducing the effort needed to maintain secure communications within your systems. 6. Compute Engine Best Practices. Control access. Use IAM roles and service accounts to control who can access your VMs and resources. It's important to avoid using the default service account as it often has too many permissions. Isolate machines. Keep unrelated VMs on separate virtual networks, VPCs, for better security. This limits the potential for lateral movement in case of a security breach. Monitor and audit logs. Use cloud audit logging to track changes and activities across your resources. This helps you understand who did what, where, and when, allowing you to detect unauthorized access or unusual activities. Patch and update. Regularly, Compute Engine does not automatically update VMs, so you need to ensure your VMs are patched and updated regularly. It's better to patch the image that was used to create the VM and then redeploy the VMs, rather than updating individual VMs. Securing cloud data. 1. Cloud storage IAM permissions and access control lists, ACLs. IAM permissions. Google Cloud provides identity and access management, IAM, to control access to resources, such as cloud storage. You can assign roles at different levels, organization, folder, project, or bucket, and these permissions flow downward from higher levels, i.e. permissions set at the project level apply to all buckets under that project. To prevent certain actions, you can use deny policies which override granted permissions. ACLs, access control lists. ACLs offer more granular control than IAM by specifying access permissions at the object level, i.e., individual files or folders in cloud storage. While IAM should be the preferred method for managing access, ACLs can be useful when fine-tuned control is required. 2. Auditing cloud data. Admin activity logs, cloud storage logs, any changes made to bucket configurations or metadata automatically. Data access logs. These track who accessed or modified data, files, but they are not turned on by default. Enabling these logs allows you to monitor how data is used and by whom. Exporting logs. To analyze logs effectively, you can export them to BigQuery for detailed analysis. This involves creating a BigQuery dataset and loading the log data into specific tables, like usage or storage tables. 3. Signed URLs and signed policy documents. Signed URLs. These provide temporary access to cloud storage without requiring the user to have a Google account. For example, you can generate a signed URL for someone to download or upload a file, valid for a specific time frame, e.g. 10 minutes. Signed policy documents. Unlike signed URLs, signed policy documents provide greater control over uploads, specifying details like file size and content type. These are useful when you need to restrict uploads to specific formats or conditions. 4. Encryption in Google Cloud. Encryption at rest. All data in Google Cloud is automatically encrypted at rest, while stored. Each chunk of data is encrypted using a unique data encryption key, DEK, which is further protected by a key encryption key, KEK. Google manages this by default, so you don't need to configure anything. Customer Managed Encryption Keys, CMEK. If you need more control, you can manage your own encryption keys using Cloud Key Management Service, Cloud KMS. This allows you to define key rotation periods, expiration, and control access to the keys. Customer-supplied encryption keys, CSEK. With CSEK, you can provide your own encryption keys from outside Google Cloud, giving you complete control over the key management. However, you must provide these keys each time you access encrypted data. Cloud External Key Manager, Cloud EKM. This allows you to use keys managed by external key management partners to encrypt data in Google Cloud. Google never stores these keys, so they remain outside Google's control, offering even more security for sensitive data. 5. Cloud Hardware Security Module, Cloud HSM. HSM. A hardware security module, HSM, is a physical device used to securely store and manage cryptographic keys. Google offers Cloud HSM, which provides a managed HSM cluster. It supports high security standards like FIPS 140-2 Level 3, ensuring that the encryption keys are tamper-evident and secure against physical threats. 6. BigQuery IAM roles and authorized views. IAM roles in BigQuery. BigQuery uses IAM to manage access to datasets and tables. Roles can be assigned at the dataset level or even at more granular levels like individual columns or rows. This enables secure access control over sensitive data. Authorized views. You can create views in BigQuery that expose only certain parts of a dataset, specific columns or rows, to certain users. This is especially useful when you need to restrict access to sensitive information while still allowing users to query the non-sensitive parts of the data. 7. Best practices for securing cloud data. Cloud storage. Best practices. Avoid using personally identifiable information, PII, in bucket names or object names, as these appear in public URLs. Use signed URLs to provide temporary access for users who don't have Google accounts. Set lifecycle rules to automatically delete or archive sensitive data that's no longer needed. BigQuery best practices. Use IAM roles to limit access to data, following the principle of least privilege. Use authorized views to restrict access to sensitive data. Set table expiration settings to automatically delete data that's no longer needed. Securing Google Kubernetes engine. Kubernetes is a system for running and managing containerized applications. It abstracts the underlying infrastructure, allowing developers to deploy, scale, and maintain applications using containers. Google Kubernetes Engine, GKE, is Google Cloud's managed Kubernetes service, providing a scalable and easy-to-use platform to run Kubernetes clusters. Key components: containers. Containers are lightweight, isolated environments where applications run. They bundle the application code and its dependencies. Pods. A pod is the smallest deployable unit in Kubernetes and can run one or more containers. Containers within a pod share resources like network ports and IP addresses. Nodes. These are virtual machines that run Kubernetes pods. Each node is part of a cluster and provides services to pods, such as hardware and networking. 2. Authentication and Authorization in GKE. There are two main types of accounts used in GKE: user accounts, managed outside of Kubernetes, typically by Google Cloud, and used by humans to interact with the Kubernetes cluster. Google Cloud Service accounts and Google user accounts fall under this category. Service accounts, managed by Kubernetes and used by pods to interact with the cluster and external services. These service accounts are more limited in scope and are bound to a specific namespace. While Kubernetes service accounts are limited to the cluster, Google Cloud Service accounts can access various Google Cloud resources outside of Kubernetes. Role-Based Access Control, RBAC. RBAC is used to define fine-grained access controls for Kubernetes resources. It enables you to assign permissions to users or service accounts to perform specific actions like creating or modifying pods. 3. Cluster Hardening Guidelines. Keep GKE updated. Keeping your GKE version updated is crucial for security. GKE automatically updates the control plane, the component that manages the Kubernetes cluster, but node auto upgrades can also be enabled for regular patching. GKE offers rapid, regular, and stable release channels. Rapid gets the newest features first, while stable focuses on proven, stable updates. Restrict access to the control plane. By default, the control plane, the primary node managing the cluster, has a public IP, which can be accessed from the Internet. To improve security, disable public endpoint access. Use authorized networks to limit access to trusted IP ranges. Use least privilege service accounts. Avoid using the default Compute Engine service account, which has broad permissions. Instead, create minimally privileged service accounts to limit access to only what's necessary. Shielded GKE nodes. Shielded nodes provide enhanced protection against unauthorized access by ensuring that nodes boot in a verifiable state, protecting the integrity of the OS. Enabling secure boot ensures only trusted software is loaded on the node. Pod-to-pod communication restrictions. By default, pods within a cluster can communicate with each other freely. However, this can introduce risks. Use Kubernetes network policies, or Istio, to control pod-to-pod traffic and limit exposure. 4. Securing workloads. Limit pod container privileges. Containers should not run with unnecessary privileges. Use the security context in Kubernetes to restrict container access and define security-related options like user group permissions for workloads. Workload identity. GKE applications often need access to other Google Cloud services, e.g., storage, machine learning APIs. Workload identity allows a Kubernetes service account to act as a Google service account, eliminating the need to manage service account keys manually. Workload identity enforces the principle of least privilege and provides strong security by automatically managing access to Google Cloud services. Binary authorization. This feature enforces that only trusted containers are deployed into GKE clusters. Binary authorization ensures that containers pass vulnerability scans and are built from trusted sources before deployment. 5. Monitoring and logging. Kubernetes Engine Monitoring. GKE includes native integration with cloud monitoring and cloud logging. By default, Kubernetes Engine Monitoring is enabled when you create a GKE cluster. The monitoring dashboard provides key performance metrics like CPU and memory utilization. You can organize these metrics using hierarchies like cluster, node, pod, and container levels. Cloud logging and audit logs. GKE also integrates with cloud audit logs, which record any administrative actions taken on the cluster. Access transparency logging provides logs that show actions taken by Google personnel on your resources, ensuring transparency. 6. Firewall Rules in GKE. GKE automatically creates firewall rules to manage traffic to and from the cluster. Ingress rules control the traffic entering the cluster, and service rules control traffic between the pods and services. Do not modify automatically created firewall rules. Modifying or deleting these rules may result in unexpected behavior. If you need custom firewall rules, create them with a higher priority than the default ones.